Hello, this is the fifth in a series of videos about mass collaboration. This video is about the Fragile Families Challenge, a research project I've been working on for the last several years. This video builds on material in Chapter 5 of Bit by Bit, so before watching it, you should watch the previous videos in the series or read Chapter 5. So in Chapter 5 and in the previous videos, I split up mass collaboration into three categories. And this video is about an example of an open call project. Okay, so this project is one that I worked on with actually hundreds of people. It was co-organized by myself, Ian Lundberg, Alex Kindle, and Sarah McClanahan, and it involved hundreds of researchers from around the world participating. In fact, some of you may have participated, and if so, thank you very much. So this project, the Fragile Families Challenge, was really inspired by Wikipedia. So Wikipedia is amazing. I love it. And one of the great things about it is, so they're able to solve this hard intellectual task of writing an encyclopedia. And they were able to do it not by creating any new knowledge. All the knowledge that was needed to create Wikipedia already existed. What they did was they had a new form of collaboration, one that was enabled by the digital age. So as we are in the digital age, we should now ask, are there other big intellectual problems that could be solved through new forms of collaboration? Even when all the knowledge that we already need to solve the problem already exists, what really is the barrier is the collaboration. So the idea of mass collaboration in science is of course not new. This is the paper announcing the sequencing of the Human Genome Project. This has 200 biologists who worked on it. This is the paper announcing the discovery of the Higgs boson. This paper has 5,000 physicists and engineers who work together to solve this problem. And these people were working together from institutions all over the world. So if hundreds of biologists can sequence the human genome and thousands of physicists and engineers can discover the Higgs boson, what would happen if we had hundreds of social scientists and data scientists working together? What could we accomplish together that none of us could accomplish individually? So that led us to create the Fragile Families Challenge. And the Fragile Families Challenge was really focused on one question: how predictable are life trajectories? That is, given some information about someone's life, how well can we predict what will happen to them in the future? So this builds on an enormous amount of research by people who have studied the life course, and that research has done things like described social patterns, theorized important factors, and estimated causal effects. But generally, it doesn't ask this question about predictability. So given all the work that we've done so far about the life course, and given a large, high-quality data set, how well can we predict individual life outcomes? So this is an example of a research project that's focused very much on predictability. And that's something that's not so common in the social sciences right now. So I want to take a step back and point out a kind of difference that exists in the social science community and the data science community. It's illustrated lovely by this idea from the Melanathon and Spies paper, Y hats and beta hats. So if you think about a regression model, there's Y hats as a function of beta hats and some data. And in social science, we generally focus on the beta hats. So you'll often see, for example, in a talk or a paper, a regression model and a statistical test about one of those coefficients. And we often ignore the Y hats, how accurately does our model predict, or how well does the model fit the data. On the other hand, in computer science, you often see a strong focus on prediction with little focus on understanding how those predictions are working. And so each of these kind of misses a little bit. So it doesn't make sense to focus only on the Y hats. It doesn't make sense to only focus on the beta hats. Ideally, we'd understand both together. And so one way to think about the Fragile Families Challenge is it's going to be Y hat in the service of beta hat. So we're going to focus on prediction, but the goal is then to use those predictions to help us build understanding. So generally, social scientists don't care about predictability of social outcomes, but I think they should. and they should for scientific reasons. So first, predictability of life trajectories is a basic social fact. If I can tell you everything about someone's life based on the conditions of their birth, that tells you something about the society that that person is living in. And so these questions about predictability are an important indicator of societies, and they vary across countries and over time. So it's a basic social fact that we should understand. The quest for predictability can lead to scientific discovery. It can help us develop new theories and help us improve our measurement. Also, there are important policy reasons that we should care about the predictability of social outcomes, especially now. So this is an article from the New York Times Magazine about what's happening in Allegheny County, Pennsylvania, which is basically Pittsburgh. So the Child Protective Services system is using an algorithm to create risk scores, which helps them decide which cases of suspected abuse and neglect should be investigated. So some people find the use of algorithms in this setting very exciting. They think it has a chance to improve the child protective system and help kids. Other people find it very scary. They're particularly worried about bias and bias in the data. So bias in the data leads to bias in the predictions, and all of this could potentially be obscured by all of that algorithmic complexity. So some people are very excited, some people are very scared. Frankly, I'm a little bit of both. But policymakers who are having to make these difficult decisions of how to weigh out and how to decide when these systems should be used, how they should be used, are lacking an important piece of basic information, which is how accurate are these predictions? Under what settings, under what conditions should we expect these predictions to be accurate, and under what conditions should we expect them not to be accurate? So however you feel about these algorithmic risk scores in high-stakes social decisions, we should expect that their use will likely increase in the future. And so scientifically, we need to be able to provide some basic facts to the policymakers who have to make these difficult decisions. So we're going to study the predictability of life trajectories using the Fragile Family and Child Wellbeing Study. This is a study that my colleague Sarah McClanahan has been working on for the last 20 years, along with a number of colleagues. It's a birth cohort panel study, which means they sampled about 5,000 children born in 20 US cities and then followed these families over time at regular intervals, collecting data from them. This data has already been used in hundreds of papers and dozens of dissertations. So this is a snapshot of what the data looks like, a schematic of the data. So there are different data collection modules, for example, survey with the mother, survey with the father, in-home assessment, survey with the child, and then there are different time points, birth, age 1, age 3, age 5, age 9. When we started the Fragile Families Challenge, the data from birth to age 9 was available to researchers. The data from age 15 was collected but not yet available to researchers. Sarah and her colleagues on the Fragile Families team were preparing the data to be used by other researchers. So when you have this data that's collected but not yet available, it actually creates a golden opportunity to measure predictability. And it's an opportunity that exists inside of every longitudinal survey that's happening all over the world. So this is an amazing opportunity that we can take advantage of. So here's how that same data schematic might look to a machine learning researcher. So we have a big matrix. We have about 5,000 families. And then if you stitch together all of the data that's been collected from birth to age 9, we have almost more than 12,000 features or variables about these families. And then at age 15, there are another 1,500 variables or features that have been collected. And so when you see something like this makes you think of doing a project using the common task method. So this is a common, typical thing in machine learning, not yet a typical thing in the social science, but it's a beautiful research design. And so here's how it works. So we pick 6 of the outcomes. So for example, the grades of the kid at age 15, and then we split those into a training set and that is available to researchers, and then some other data that's not available to researchers. So there's actually 2 data sets that are not available to researchers, the leaderboard set and the holdout set. For our purposes here, the leaderboard set is not very important, so we're going to focus on the holdout set. So here's how that same data schematic might look to a machine learning researcher. So we have a big matrix. We have about 5,000 families. And then if you stitch together all of the data that's been collected from birth to age 9, we have almost more than 12,000 features or variables about these families. And so when you have this data that's collected but not yet available to researchers, it actually creates a golden opportunity to measure predictability. And it's an opportunity that exists inside of every longitudinal survey that's happening all over the world. So this is an amazing opportunity that we can take advantage of. So So what happens during the challenge is researchers can use the background data that's collected from birth to year 9 to try to build a model to predict the training data. So for example, given all the data collected from birth to year 9, build a model, let's say a regression model, to predict the grades of the kid in school. And then use that model to predict the holdout data. And then anyone can use any technique they want. They can use statistical models informed by social science theory. They can use machine learning models that don't pay attention to social theory at all. They can do whatever they want. And then in the end, we're able to compare all of these approaches in a fair way by seeing how well they predict the holdout data, the data which they don't have access to. So this is a really good way to produce credible estimates of predictability. Because if the results are very predictable, there's no way that can be explained by overfitting or researcher degrees of freedom or other researchers kind of doing funny things, because we, as the organizers of the challenge, held the holdout data. No one had access to it while they were participating. So if the results are very predictable, then there's no way that can be explained away. Likewise, if the results show low levels of predictability, that also can't easily be explained away. So if I did the challenge by myself and I was not able to predict GPA very well, you might say, well, Matt, you don't know very much machine learning, or Matt, did you try this technique or that technique? But if hundreds of researchers try and the best results have low levels of predictability, it's much harder to dismiss. So the challenge produces a good way, a design that produces credible estimates of predictability. So now let's talk about the outcomes that we picked. So these were outcomes we worked with Sarah and her colleagues, domain experts, people who have spent their careers studying the life course, particularly for disadvantaged families. So the outcomes we picked were characteristics of the child, the GPA, the grades of the child, the grit. Grit is a psychological measure that measures perseverance and persistence. Also, some were properties of the household, so eviction, whether the household was evicted, the amount of material hardship the household experienced. So material hardship is like a measure of experienced poverty. It's a scale that includes questions like, have you ever gone to bed hungry? Were you ever not able to go to the doctor because you couldn't afford it? Things like that. Finally, some of the outcomes are about the primary caregiver, whether the primary caregiver participated in job training, whether the primary caregiver had job loss. So 457 researchers applied to participate. Many worked in interdisciplinary teams, so teams that were mixed of social scientists and data scientists. So this leads us to this question. Using a large, high-quality social science data set collected since birth and modern machine learning methods, how accurately can we predict outcomes for children, parents, and families? And so the results I'm going to show you are measured in terms of this metric, R-squared holdout, which is the R-squared on the holdout data set. So there's two important benchmarks to keep in mind. 0 would be where the predictions are no more accurate than predicting the mean of the training data. So that's kind of like a null prediction. If you want to predict the grades of all the kids by just saying, well, the average grade in the training data was 2.87, so I'm going to predict 2.87 for all the kids. That's the null model. So if the prediction is no more accurate than that, the R-squared is 0, and if the prediction is perfectly accurate, then the R-squared is 1. So hundreds of researchers participated with this data that was collected over the course of a very long time, and let's see what happened. So these are the R-squared holdout values. So for material hardship and GPA, we see R-squared of about 0.2, and for the other outcomes, we see R-squareds close to 0. So this is one way that you might look at this graph. Let me show you the way I think we should look at this graph. So rescaled to go between 0 and 1. And so everything in the Fragile Family study, plus all of our ideas, plus modern machine learning, that gives us what's in the blue bars. And what we see in this graph is that the dominant pattern is this vast gray space. So it seems to be the case that there's a lot happening in the lives of these families that's not accounted for by a high quality data set and modern machine learning techniques. So when you see, and let me just say one more thing, this is for the best prediction. This is for each of these variables. So many of the submissions are actually much worse than this. Now, when you see results from a complicated prediction, it's often good to compare this to a simple benchmark model. So how well does this do compared to something that doesn't involve all of these variables and fancy machine learning? So to assess that, we created a simple model using regression, linear regression or logistic regression, using 4 variables selected by a domain expert. And so these are the results from the best machine learning model with access to all of the variables. Here's the results from a 4-variable regression model. So you can see that the very best machine learning model does better than the 4-variable regression model, but not substantially better. So if your intuition is having access to all these predictors and using modern machine learning methods will lead to qualitative improvements in predictability, that's not what we saw here. So what does an R-squared of 0.2 look like? Here is a scatter plot, which I think helps illustrate it. So here we're seeing 2 things, the benchmark model and the best submission. So let's look at the best submission for a second. So the x-axis here is the truth, which goes from 0 to 1. This is for material hardship. The y-axis is the prediction. So if the predictions were perfect, everything would lie along the 45-degree line. And we see that's clearly not the case here. The dashed horizontal line here, this is the mean of the training data. So what you can see is if your intuition is that the best submission is going to be something like the truth with some error, that's not really what's happening. What's happening here is that the best submission is really just predicting the mean of the training data with a little bit of signal. So for the cases where the true material hardship is high, it's generally above the mean of the training data. For cases where it's low, it's generally below, but it's not qualitatively different than predicting the mean of the training data. And then if you look at the benchmark model, again, this is the 4-variable regression model, it looks qualitatively very similar to the best submission, even though the best submission was substantially more complicated. So this is what an R-squared of 0.2 looks like, and those patterns in the predictions, we also see those in the other continuous outcomes. So again, we see the best submission looks roughly similar to the mean of the training data, and the best submission does not look qualitatively different than the benchmark model, the 4-variable regression model. So now let's look at the results for binary outcomes. So these are the results for eviction. So let's look at the best submission. So we see those 2 histograms. So one histogram where the event occurred, those are for the families that were evicted. And so if the models were working really well, the predictions would be very close to 1 for the families that were evicted, and then very close to 0 for the families that were not evicted. And what we see is, in fact, the predictions are actually pretty similar for the families where the event occurred and where the event didn't occur. Again, we see something where most of the predictions are close to the mean of the training data with some signal. So it's true that the best submission for the cases where the families were evicted, you see a slight shift to the right. And for the cases where it didn't happen, you see a slight shift to the left. That's a sign that something is happening. But you see this not doing a very good job of separating out the cases where the families were evicted and where they were not evicted. And like the previous graph, we can also compare the best submissions to the benchmark, and we see that qualitatively these are quite similar. So now we can look at all the binary outcomes, and again, we see similar pattern. The best submission is pretty similar to the mean of the training data, and the best submission is qualitatively pretty similar in performance to the benchmark model. So those results were all about looking at the best submission, how well it does in absolute terms, and how it does relative to a benchmark model. Now, in this mass collaboration, though, we actually had many different submissions. So what can we learn by looking at the pattern of all of the submissions? So this heat map shows the pattern of squared errors. So Each column here represents a family. Each row represents a team that was participating in the challenge. And the intensity of this heat map shows the amount of the squared error for that team's approach to predicting that family. And so what you see here is that there are some families that are very poorly predicted by all of the teams. That's the dark purple in the graph. But they're the big, like, kind of cream color. There are many families that are predicted well by all of the teams. So if your idea was that some machine learning techniques are going to work really well and others aren't going to work really well, you would see a lot of variability based on which team was making the submissions, because these teams use very different techniques. We can see that from a survey that they filled out and all of the code which they've open sourced. And so even though these teams use very different approaches, they all produced relatively similar predictions. And so we see there are some families that are poorly predicted by all of these approaches and other families that are well predicted by all of these approaches. So there seems to be more important variability in the families than there is in the machine learning techniques. So here are the results for all 6 outcomes. And again, we see broadly a similar pattern where there's much more variability across the families than there is across the techniques. So the fact that all these different techniques were used and produced, to a first approximation, the same predictions leads me to wonder whether it's possible for any technique to yield better predictions that are, or qualitatively better predictions than what we saw in the challenge. So what did these results mean for policymakers? So I think an important takeaway here is that machine learning is not magic. Just because you use machine learning does not mean the predictions are going to be accurate. I know that's an obvious thing to say, but I think there's a belief among some people that if machine learning is used, then the predictions must be accurate, and that's just not true. Second, it's very difficult to anticipate when predictions will be accurate and when they're not. I've showed the results of the challenge to many people, experts in machine learning, experts in the life course, and there are very different ideas about how accurate these predictions would be. And so what we see is that even for experts, it's hard to anticipate, and so transparent evaluation of any algorithm is needed. And then the third lesson for policymakers is that complex models may not outperform simple models. So you may have the idea that the more complicated the model, the better it will do. That actually was not the case during the challenge. So many of the models actually did worse than the 4-variable regression model. And so complexity doesn't always lead to better performance. So what do these results mean for researchers? So I think there's a whole different set of things. So I think the main consequence for researchers is that we have to reconcile what we're calling this understanding prediction paradox. That is, researchers believe that a lot of understanding has been generated from this fragile families data, as evidenced by more than 750 published research articles. But yet, these data could not be used to make accurate predictions of important life outcomes. So it seems kind of strange that these data are able to yield so much understanding when they're not able to be used for prediction. So we see a couple ways this could be reconciled. The first is we can conclude we actually don't understand that much about the life course, and it can call into question really how much we know. A second way to resolve the paradox potentially is to decide that prediction is not a good measure of understanding. And a third way to resolve the paradox is to believe that our current understanding is correct, but it's incomplete. So for example, maybe it's the case that we're actually measuring the important predictors of life trajectories, but we need new theories about why we shouldn't expect predictability of life trajectories. So for example, in the context of the weather, even though we measure lots of things about the atmosphere, we don't expect perfect predictability of the weather, especially over long timescales. And that's because there's a theory in meteorology to say why we should not expect perfect prediction. And so maybe what we need is something like that for the life trajectory. Maybe that is the way that we can resolve this understanding prediction paradox. So how can we improve our understanding? One way that we can do it is with in-depth semi-structured interviews. So at the beginning, I talked about Y hat and beta hat and how we were going to use the predictions to help us do understanding. And so one way we're doing that is we're interviewing the kids and families to try to learn more about their lives. And we're particularly interviewing the people whose outcomes were hard to predict. And so let me explain this. So one way to look at these results is that there is a lot of stuff out there in the world impacting people that we're not currently measuring and theorizing. And so we are calling that stuff dark matter, kind of in an homage to astronomers. And so the idea is we want to go and find that dark matter. What is this other stuff that is impacting these people's lives? And as there is a great way to learn about this. So this is what are techniques that we can use to find out about things that are not actually in our data set. So I don't know of any machine learning technique that can help us discover things that are not in our data. But in social science, we have that technique, and it's called talking to people. And so what we're doing is we're finding the families that are poorly predicted by the best available data and the best available model. We're finding kids and families who are doing better than expected. We're finding kids and families who are doing worse than expected. And we're finding kids and families who are doing as expected. And we're doing in-depth interviews with them to try to understand what are these potentially important and unmeasured factors. So this is an example of how prediction can help us lead to understanding, because the prediction will help us target our interviews to the families that are likely to be most informative. And so you could imagine doing this over and over and over again, hundreds of times. So you have a systematic longitudinal data collection, you do predictive modeling, you do in-depth interviews, and then you learn some more, you improve your data collection, and if you do this over and over and over again, you would potentially learn a lot. So that's a little bit about the Fragile Families Challenge. This is a paper that we've recently published, and I would also recommend reading the accompanying commentary by Feliz Garip. Also, there is a special collection of the journal Socius about the Fragile Families Challenge that includes 12 manuscripts submitted by challenge participants, all of which have an accompanying code and computing environment to make the results more computationally reproducible. There are also 3 papers by our group. One is that we hope will make it easier for other people to do similar mass collaborations. So one is about the privacy and ethics process that we went through. One is about the ways we've tried to improve the survey metadata to make it more amenable to predictive models. And one is about the successes and struggles that we had with computational reproducibility. That is, as we were editing this special issue, we wanted to make sure that all of the papers had code that could be used to reproduce their results. So that's a little bit more about the Socius Special Collection. And stepping back from what we've done, I think it raises, again, questions about what is the role of prediction in the social sciences, and what are the kinds of things that we could accomplish together that none of us could accomplish individually. How can we use mass collaboration to help us advance scientific research? So this is the final video in a series of 5 videos about mass collaboration. Thank you.